This is Professor Derf. Cites. This algorithms video is about algorithms analysis. Algorithms have attributes that are desirable. Correctness is foremost. An algorithm that doesn't work is useless. It needs to work for all possible inputs. It must also validate the input and reject invalid input. Algorithms must be efficient in terms of their runtime performance, their time usage, and their memory usage, their space usage. The efficiency perspective is the main focus of this presentation. Also, the data itself varies from various states of data, how it's the content of the data and the organization, and that can affect the efficiency. And we'll look at worst, average, and best cases for that input data. Algorithms must also be easy to understand so they can be maintained and have a useful lifespan to allow them to be easily changed over time as new requirements and regulations come into play. Lastly is the concept of elegance, aesthetically, artistically pleasing algorithms. That's a lower priority than these first three. One way to determine an algorithm's efficiency is by experimentation, running it and timing it. But this is flawed by confounding factors. It depends on what hardware platform and what software platform. You'll get different results based on different platforms. And also, again, what data are you going to use to test it, to decide how it runs. The concept of benchmark data sets. Different people have different opinions about what should be used as a benchmark data set. Also, in order to do experimental analysis on an algorithm, it has to already be implemented. And it's desirable to be able to analyze an algorithm itself before investing in the time to go and implement it. So experimental is not really going to work. It's useful later in terms of testing the implementation, but we're looking at the design stage here and how we can analyze things at that point in time. The algorithm's inherent work analysis is the preferred method. In this method, we count the inherent units of work, and each of them are counted equally. The inherent units of work are primitive pseudocode operations broken down into input, process, and output. So any input operations, output operations, and in terms of processing, assignment, calculation, comparison, and function call and return are all units of work that we can count equally, even though in reality they do take different amounts of time. The count of units of work will depend on the input size of the data, indicated here by the variable n. We will be looking at inherent work functions of the form f of n that take the input size as input and produce the amount of work in terms of the count of the inherent primitive operations. We're mainly concerned when n, the size of the input, becomes very large. That's where problems will show up. This is formally called asymptotic analysis. I like to call it the end zone behavior. Here is a football field. Yes, I'm an Auburn graduate. And has a number line down here. Of course, the input size is only positive. There's no negative, but showing both end zones here for symmetry. We are interested in the magnitude of an algorithm's inherent work function as the algorithm's input size n gets very large. As n gets very large towards in the direction of positive infinity, we're in this end zone over here. That's our focus. How do the algorithms behave when they have a large number of items? End zone behavior. We find that there's orders of magnitude that form a spectrum, and it's a spectrum of inherent work functions. It runs from the least work to the greatest work. In the end zone, a higher order dominates and outshines all lower order growth contributors. Analogy here is from space with our own solar system. From far away in space, the sun outshines the earth and the moon. If you're far away and you see the sun as a star, you're going to see its light dominating. Even though some light from the earth and moon will be there, it's virtually zero in the scheme of things. In terms of functions, we see this concept with polynomials, for example. Here's 5x squared plus 3x plus 12. In the end zone, as x, as the value of the input variable increases very large, the x squared will dominate the behavior of this function. Its coefficient is not the main factor, and the linear term is not a main factor. In the end zone, it's the x squared that will dominate the behavior, and that's what gives us one of these functions in the orders of magnitude spectrum, these dominating functions. So in the picture here, we have lower orders, such as this Earth and the Moon on the left here, and then towards the higher orders, the Sun, spectrum of functions, orders of magnitude functions. Here is a list of the primary order of magnitude functions used in computing, and they go from the lowest order at the top, constant, to the highest order at the bottom, exponential. The name of the functions: constant, logarithmic, linear, n times logarithmic, called n log, quadratic, cubic, and exponential. Here are the function definitions. F of n equals a constant c, and we have a notation called big O notation for order of magnitude. That's order of c. F of n is log base 2 of n. Base 2 is a common occurring base in algorithms in computing. That's the one we'll use. That's order of log n. It's implied there that base 2. F of n equals n. It's linear. Order of n, n log base 2n, order of n log n. And you can see that for each function, it's indicated by its order of magnitude with this notation here, a big O, and in parentheses, the dominating function for that level. And keep in mind that the lower orders at the top and the bigger orders are at the bottom. The greatest one is exponential, the least one is constant. Here we have the unit of work comparison for these 7 orders of magnitude functions for various input sizes, starting with small sizes 10 and going up through 1,000,000. 1,000,000 is in the end zone. We can have bigger inputs than that, but we want to consider what happens when we have 1,000,000 items, either from a database or whatever that we have to look at. And notice what happens here. If we look at 1,000,000, the number of units of work for for the lower orders are very small. Here we get into linear as a million because it's going to match the input size. And then they start going up. Quadratic becomes quite large, number of units of work there. And cubic is extremely large. And exponential, this E notation is 10 to the power. So here we have 10 to the 30th power, 10 to the 301st power. That's 301 zeros after a 10. And for a million, the calculators can't even handle this. Microsoft Excel, it was an overflow, arithmetic overflow. It's beyond what can be calculated and shown. So the higher orders must perform significantly more work than the lower orders. That means their performance is going to be slower in terms of the time. Here's some time comparisons. The assumption here is that we have 1 billion operations per second on some fictional machine, and that equates to this many operations per hour. Some huge giant number of operations per hour. And we look at input sizes here, 1 million and 10 million for the various orders of magnitude functions. And this is in hours, this chart. Look down here for quadratic. When you get to 10 million, it's 28 hours to do the work. 28 hours for 10 million items. And then when you get down to cubic, for even 1 million items, almost 300,000 hours. And this is unrealistic. Might as well just forget it. And exponential, these are hours. Look at that, 10 to the 288th power hours just for 1,000 item input. Cannot be done. It's totally impractical. Higher orders take significantly more time than lower orders. You can see the clock here with the flames coming out the top. These higher order algorithms are just burning up time, precious resource that we don't have, just a limited amount of. Graphically, if we compare the 7 orders of magnitude here, the one that looks like the smallest in this graph is the logarithmic base 2. However, it is increasing. We'll see in another slide that it overtakes the constant one. Actually, the constant, for any constant value, it doesn't matter what it is the lowest of the orders because it's not increasing. All the others increasing. So in the end zone, when you get far enough with a big enough input value, they will rise above it in the units of work that they do. So the real order is constant, logarithmic, linear, n log, n times a log, quadratic, cubic, and exponential. And here it appears that perhaps cubic is overtaking exponential, but again we have to look in the end zone to see what really happens. For the constant and logarithmic, we see that for input sizes greater than 1024, logarithmic order base 2 overtakes a constant order of 10. And here, for input sizes greater than 9, exponential order base 2 overtakes the cubic order. Exponential does quickly, only greater than 9, and it's already overtaken it. Input cases, the time efficiency is dependent on the content and organization of the input data. There are 3 cases. Best case is when the input results in minimal runtime, Average case is an average runtime, and worst case is a maximum runtime. Consider a sequential search algorithm. The best case is when the search key that you're looking for is the first item in the list and it gets a hit right away. The average case is if the key is somewhere in the middle, and the worst case is when your item is at the very end of the list. We should design our algorithms and select from choices based on the worst case input scenario, because when that happens it still has to be realistic that we can run the program that's created from the algorithm and it will finish in a realistic amount of time. Looking at some of these in more detail, constant time is the lowest order. It always takes the same fixed amount of time regardless of the input size. It doesn't care about the input size. But it's overtaken by all the others because the other ones are increasing and the constant has a slope of 0. An example is accessing an array item via an index. It just takes 1 unit of work. It's order of 1. Logarithmic time, base 2 is the slowest increasing growth rate. It beats constant, but it's slower than all the others. To understand what a logarithm really is, it's this statement right here. A logarithm is an exponent. It's the exponent to apply to the base, in our case 2, to get the input size we're interested in. For example, log base 2 of 32 is 5 because 5 is the exponent that you raise the base 2 to get 32. Base 2 is the most common base used in computing algorithms. It appears in patterns of continued division by 2. When you're dividing something in half and then taking halves of that, that's a logarithmic growth rate. A binary search algorithm is order of log n. Linear time has a growth rate of 1 work unit per input item. A loop that iterates n times is order of n. The find minimum and maximum algorithms are order of n. It depends on the size of the input. They have to look through everything to find the minimum or max. And the sequential search algorithm is order of n. N log n, it's linear times something. It's sandwiched between linear and quadratic time. The merge sort algorithm has this order. Quadratic time is proportional to the square of the input size. It grows rapidly. A nested loop inside another loop, both of which iterate n times, is order of n squared. The bubble sort, insertion sort, and selection sort algorithms are all order of n squared. They're all quadratic. Cubic time is proportional to the cube of the input size. It grows very rapidly. A nested loop inside another, inside a third, all of which iterate n times, has cubic time. Exponential time is the fastest increasing growth rate. Its growth is too rapid to be of practical use. A loop that doubles its number of statements for each iteration is order 2 to the n. Other orders, polynomials. A polynomial in standard form, such as this, is order of x to the n. Its leading term minus the coefficient dominates the behavior of this polynomial in the end zone for very large values of x in this case. examples: 17x to the fifth minus 45x third plus 100x squared. We see some various coefficients here, but the x to the fifth is dominating the behavior of this polynomial. 1000x squared is still order of x squared. It's the x squared that's going to dominate in the end zone, not the fact that there's an 1000. And this one, x to the third, even though these other terms have very large coefficients, in the end zone behavior, its order is cubic. So it's quite simple. You find the dominating term and don't consider the coefficient or the other terms because we're looking at the end zone. It's very simple to pick out which order it is. There's composite orders as well. When multiple different orders appear in a sum or difference, the highest order again trumps or outranks the others. Here we have a mixture, a linear term, a log term, and linear is a higher order than log. It's going to trump, so its order is n. Here's an exponential term with a cubic and a linear. Exponential is the highest. It's going to trump everything else, and the order here is exponential. We're not so much focused on space requirements in this presentation, but want to point out that frequently time and space are inversely proportional. That means decreasing one requires increasing the other. Here, if we want time to be minimal, we're looking at a larger memory space requirement. And if we want space to go down, time has to go up. In summary, given multiple algorithms that correctly solve a given problem, use the one that has the lowest order of magnitude for the worst case input. In any case, it must complete its processing in an acceptable amount of time. And to improve an algorithm, focus on lowering its order of magnitude. This concludes this video.